Okay, let's just dive right into this explainer. If you've ever stared at a really complex differential equation and just thought, well, I've hit a brick wall, you are absolutely in the right place. Today, we're going to explore how to conquer seemingly impossible calculus problems by essentially shifting them into an entirely different dimension. We're using the Laplace transform not just as some boring formula you memorize, but as an actual translation tool to turn a complete calculus nightmare into a total algebra breeze.
Because this is a pretty dense mathematical journey, here's our roadmap. We'll start with meeting the monster equation, check out the Laplace transform magic, navigate the S-domain, hit the integrating factor, return to reality, and finally get our final answer.
All right, let's kick things off with section 1, meet the monster equation.
I know. This looks like a massive wall of math right off the bat, but hey, don't panic. We're going to isolate and conquer this thing line by line. This whole process is basically the complete life cycle of a complex problem being broken down into really manageable algebraic steps. Our goal today is to understand exactly how we get from that daunting initial problem all the way down to a neat, clean answer.
So the crucial point here is identifying our monster. We've got a second-order differential equation, but the real issue? Our derivatives are multiplied by t. It's those t variables sitting right next to our y double prime and y prime that make standard calculus approaches literally a nightmare here. Oh, and we also have our initial conditions, y of 0 equals 1 and y prime of 0 equals 1, which are going to act as our anchors later on.
Our very first move is just simple prep work. We're going to expand that equation so every single piece is clearly separated before we try to transform it. By distributing the y prime into the 2t plus 1 and the y into the t plus 1, we're basically laying all our cards on the table. Sure, it looks a little longer now, but this separation is absolutely crucial so we can apply our transform rules cleanly to every individual term.
Which brings us to section 2, the Laplace transform magic.
Now, this isn't just a standard mathematical operation. It literally changes our functions from y of t in the real world to f of s in, well, an alternate dimension. Think of it like taking a really difficult, dense text and translating it into a language you are perfectly fluent in. By applying this operator to our equation, we are fundamentally changing the rules of engagement.
And by making this jump, we completely leave the hard calculus behind and enter a universe where the rules are just basic algebra. In the t-domain, dealing with derivatives multiplied by variables is just messy. But over in the s-domain, those derivatives transform into simple polynomials of s. It is such a powerful trade-off.
Moving right along to section 3, navigating the S-domain.
So we apply the transform to our expanded equation. And here is the really clever trick of Laplace. Whenever our original term was multiplied by t, that becomes a negative derivative with respect to s in the new domain. We apply this rule to each piece, and at the exact same time, we go ahead and substitute in those initial conditions we were given earlier.
Now, what I absolutely love about this step is how those initial conditions just immediately plug right in, turning y of 0 and y prime of 0 into simple 1s and negative 1s inside our brackets. We're executing the derivatives with respect to s on the terms that used to have a t, while the terms that didn't have a t simply drop their f of s equivalents right into the mix.
And look at how beautifully this simplifies. Once we group our f of s and f prime of s terms together through standard algebra, we end up with a much cleaner first-order equation. Notice how those messy polynomials factor down into forms of s plus 1? We've successfully wrestled that second-order monster into a totally manageable first-order algebraic expression.
That leads us nicely into section 4, the integrating factor.
Okay, so we've got a much cleaner equation now, right? But how do we actually isolate and solve for f of s? This brings us to a critical pivot point in our journey. We have f prime of s and we have f of s, but they are all tangled up with those s plus 1 coefficients. We need a systematic way to untangle them so we can actually integrate.
So to get standard form, we divide out that leading term sitting in front of f prime of s. We need that coefficient to be exactly 1. Once we do that, we set up our integrating factor, mu of s, by taking the exponential of the integral of our f of s coefficient. And the math here is honestly just elegant. The exponential and natural log cancel each other right out, simplifying beautifully to just s plus 1.
This right here brilliantly illustrates the magic of the integrating factor. It collapses the entire left side of our equation into a single clean derivative. Seriously, this is just the product rule working in reverse. By multiplying our whole equation by s plus 1, the left side magically becomes the exact derivative of the quantity s plus 1 times f of s.
From there, we just integrate both sides. The left side simply drops the derivative, giving us a straightforward integration on the right. Of course, we have to remember to add our constant of integration, c. That's vital. Finally, we divide by s plus 1 one last time, and boom, we have completely successfully isolated f of s. We've solved it in the s domain.
But we aren't done yet. Section 5, Returning to Reality.
See, we won the battle in the s domain, but that answer isn't much use to us sitting over there. We need to use the inverse Laplace transform as our portal back, applying it individually to the two clean fractions we just derived. Just like we used our rules to get here, we use the inverse of those rules to get back. The term with the squared denominator translates to a t multiplied by an exponential, while the simpler denominator just gives us the exponential. Stepping back into the t domain, we get this beautiful, nearly finished equation. Y of t equals 2t times e to the negative t plus c times e to the negative t. We've officially escaped the s domain. We have the general form of our answer, but we still have that unknown constant c hanging around.
Which brings us to the final stretch. Section 6, the final answer.
This is where we claim our prize. We refer back to the very beginning, using that starting condition y of 0 equals 1 to nail down our constant. When we plug in 0 for t, that entire first term disappears completely because of the t multiplier. The exponential in the second term becomes e to the power of 0, which is just 1. So we're left with 1 equals c. So simple, so satisfying.
We plug that 1 back in for c, factor out the common e to the negative t, and we arrive at it, our beautifully simple final solution. We literally went from a massive, complex second-order wall of differential calculus all the way to a clean, single-line algebraic function.
You know, it really makes you wonder, if shifting dimensions can turn a literal calculus monster into simple algebra, how many other insurmountable problems become easy once you learn to look at them in an entirely different domain? The Laplace transform proves that sometimes the best way to solve a hard problem isn't brute force, but just finding a smarter perspective. Thanks for joining me on this explainer, and keep looking for those new dimensions in your own work.